Hello and welcome to another RSL15 feature demonstration. My name is Taylor. Today we're going to be looking at our power consumption and battery estimator for the RSL15. Let's get into it. Thanks for being here, Brandon. You are going to show me a tool that you created that's going to calculate how much power our device is using and then estimate how long it'll be able to last off of a given battery size.
Yeah, thanks, Taylor. So we made this tool to demonstrate the battery life capabilities of our RSL10 and RSL15 products. A lot of times when customers are making solutions, the first thing they're defining is their Bluetooth operating parameters. And this tool is intended for a way for them to evaluate the power consumption of the devices, given some rough parameters of their Bluetooth operating. Some of the calculations can get up to the multiples of years of battery life. So as you can see on my screen, we are starting at the onsemi landing page. And to get to our community forums where this tool is hosted, you'll want to open the support dropdown. And on the left here, you'll see the technical support center, where under that you can see community forums. Once you open this, you'll be greeted with a bunch of different options for navigating between the different subsections that the forum are broken up into. And this tool, as it pertains specifically to our Bluetooth parts, is housed within the wireless connectivity section. So if we select that product form area, it will redirect you to topics specifically related to wireless connectivity. And you can see for an ease of access, we have pinned it to the top of the list, the RSL10 and RSL15 power consumption and battery estimators. When you open this, you'll be greeted with different articles. The first, where it actually is called the tool, is where you can download the Excel spreadsheet from, which is how this is shared with you. But this also comes along with a complimentary power consumption evaluation guide, kind of giving you a higher level overview of how we calculated these numbers and some of the measurement procedures we followed to make sure that these are accurate estimates that we're giving you. You will have a brief introduction here going over the purpose of the tool. And downloading the tool itself is as simple as finding the Excel file within the link. Clicking this, your browser will automatically download it for you. And then you're greeted with the Excel file and the landing page here, where the tool can actually be navigated and utilized to evaluate your Bluetooth parameters. If you want to just quickly dive into things and you don't care about the underlying models or some of the calculations happening in the background, we've provided 3 easy to access buttons on the landing screen here, one for each of the different Bluetooth operating modes you might care about. We have your connectable advertising, your non-connectable advertising, and your connected modes for the peripheral device. So to give you an example of how these UIs can be used, when you click on the button, there is a user forum that is automatically opened. The background will also navigate you to the sheet that is housing the models automatically. And from here, you can input all of your high-level Bluetooth operating parameters that you might configure for a device. So hitting calculate, it will take all of these input variables and plug them into models in the background that were measured on real devices to generate calculations and models that will give these numbers. So as you can see with our generated input, we have an estimated battery life of 0.23 years. This is probably a little bit lower than expected, considering we came into this talking about years of battery life. But this is pretty respectable when you consider the fact that you're sending out data every 40 milliseconds. So just to give you an example of maybe a more real-world use case where you're communicating data every 1 second, it can extend your battery life to 5.5 years.
Why don't we move back over to our demo and we'll do some measurements. We'll try to prove and see if this actually is right. Can we, what kind of battery life can we expect from what we put together? And, will that actually be what we get?
Sounds good.
Okay, so we're back to the test setup we had in our last video, but essentially we have 2 devices, and this one right here is measuring light coming in off of a photo sensor. And if it goes above or below a certain value, it's going to send an advertising packet that'll tell this one to turn its LED on. So right now, if I cover it with the light, the LED turns on, it turns off, on, off. All right, so we are set up now. I have my device being powered by my Joulescope, and we can measure and see what's going on. So the way this calculator works is by putting together what the actual advertising interval looks like.
Yeah, no, that's right, Taylor. Those models that we talked about earlier, that's all that this is based off of, is that we are characterizing each part of this advertising event, making up linear models to describe how, like you said, the transmit time might extend. If you're sending a larger packet, you need more radio time to send out that data. And by taking these building blocks within the models and reassembling them into one total estimate, you're able to make an accurate estimate just given the simple input parameters and how they relate to each of the different functional aspects of the advertising events.
Okay. So we can see now here how the diagram here, what it's coming from and what it's actually describing. So if we jump over here, there's a lot of different numbers being calculated. You can look at it more in depth and go back and forth and see, what these are exactly referencing. The main power is coming out of the TX payload. So for me, I think these are two of the big numbers we should probably verify. So let's play with this a little bit. I'm going to put in the voltage as 3 volts. Brandon, I think you said the packet size we're sending here is 30 bytes. And we have, so your typical coin cell battery 2032 that fits into our board. It has a typical capacity of 240 milliamps. So we'll go with that. Actually, so okay, before we get into this too deep, we want to just look at a couple little things. So the calculator is going to be for just our device by itself. So in this scenario, my photo sensor is actually consuming a little bit of current, but let's just take a look. So right now, if I disconnect it and our device is asleep, we actually see we are all the way down. So we are in the 110, our average 112 nanoamps. That's sleep current. So in our calculator, you see we actually even have a higher value there, 186. So we're doing pretty good. This might partly be a couple software upgrades, or the device I'm using is not a super high precision. But so the board on its own, the power sleep mode power consumption is what our calculator is expecting. But let's just put in our sensor and see what's happening in our actual use case. Here it looks like, okay, we're at more of about 6 microamps. And we can actually see how this changes. So if I completely cover the sensor, our sleep current now, we're down at about half a microamp. Then when the sensor is lit up, okay, our sleep current now is at about 6.8 microamps. Let's come back to these two numbers. I want to just verify if these are right. These are what I think are the important ones. So I'm going to trigger the device going off, and let's zoom in on one of these and see what we have. If I come in and do some measurements, I get a look at the payload time. About here, I'm getting about 362. Okay, that's pretty great. That is almost exactly right. Okay. And what is the current? 4.7, about 4.8 milliamps. And okay, again here, our average is showing about 4.1. But like I said, this doesn't actually include our sensor current. So I'm just going to quickly modify this a bit. I'm going to add a sensor current section. Sensors consuming, which right now, again, about 6 or even 7 microamps. So let's be honest, let's say it's 7 microamps, and that's how much we're consuming when we're asleep. Okay, so we've put in our sensor current, but the advertising we're simulating is 1 packet every second. And whenever we make a transition, you send 10 packets because we just want to make sure it's received, it's heard by the other device. So I think by that logic, so once a second, instead, if we measure our packet over 10 seconds, they should have the same current. Okay, so let's take a look. So this is our little burst of 10 packets. And then we go to sleep afterwards. And we calculated our sleep current. Again, even here, it's actually 6.6, 6.78. We're being a bit conservative, but hey, let's just do that. And what are we seeing? The calculator down here. So one of the main values it's calculating the battery life off of is the average current. So right now here it's saying the average current would have been 14-ish microamps. Okay, if we look at the value right here, it's saying over this 10-second period, which we were saying is equivalent, the average current is 13.6 microamps. So that is kind of dead on. Okay, Brandon, I think we've proved that this calculator actually reflects the reality, right? So what the numbers that are giving me here, I believe it.
I think you explained it well there too, Taylor. The fact that these numbers line up, the fact that we pulled together a real world demonstration on the actual hardware, and acted as a proof of concept that these numbers are accurate. We hope to instill confidence in our customers that when they're using these calculators, they can get a very accurate estimate of what they will experience as far as power consumption when they start evaluating the RSL 15 or 10.
All right, and that's all for today's video. Thanks again to Brandon for helping me put this together, and you can see the description below for links to a lot of the other topics we covered today. Once again, check back soon for more videos.